We are the boss hijackers.
Y aparte que no me gusta.
Ah, no sé, ya sabes.
Vamos a los cenotes en vez de Augsburg. Parece que vamos despiertos.
El reto va a ser a ver quién se queda despierto más tiempo.
Al rato todo roncando.
This is the bad boss. ¿Qué pasó, muchacho? ¿Cuántas horas planeas dormir?
2, las del camión.
Bien. Hola, Alicia.
Hola.
¿Qué pasó?
¿Qué pasó? Ay, eso sí viene bien preparado. Sí. Good morning. Good morning. Una iguana en medio de las... Ajá. Había otra en la segunda entrada de allá. No, casi no.
Dostaneš to dokola. Budem mu to aj zvýskať, neverí. Don't believe us.
Ajá. Eco.
Ik maak al een Facebook account aan.
On the table.
You're right, it's up.
Up.
You're...
Sí, bien. We need to put those things out. Vamos a hacerlo nosotros. Nos vamos a tardar más en serio. Okay. So, the game is like this. I begin, sorry, and I say
One touch.
one touch is the table.
Then it's his turn because it's on clockwise direction.
Okay. So, if I do this, he do that.
I do this, but if someone do, then direction turns change.
Direction change.
If you made a mistake, somebody made a mistake.
Out the hand that
Made a mistake.
made the mistake.
You lose your hand.
For example, he makes this. So it is my turn again because we changed the direction. So if I don't do this, I take my other hand or something like that, I put out that hand. Yes.
But we have to start with right hand.
Depends.
It depends because, for example, I will start with this one. But if he do 2 times like this, we are going to come back and use the other.
Okay.
Yes. So every left and then right. Every time that someone this, it's turn in the other side.
One
Okay?
continues to go back.
And
Exactly.
when you change the hand, use this hand, like this hand.
One continues to go back.
Exactly. That's all. Yes. Okay. And this is very fun.
Now first.
Ahí se equivocó por ahí.
Oh.
No, pero desde que hiciste doble iba para acá atrás. Ajá. Yeah. Okay. Okay. If you have your two hands like this, you continue with the circle. For example, if his hand is not here, I use this one and then this one. Okay, because we need to continue the circle. So if your partner moves,
You start on the one touch.
start with this one. Dos o uno. Dos.
Estás aquí como
I
arreglada.
learned really quickly. Don't say that. Don't say
Who gave
that.
the idea originally? Whose idea was that? This game.
Who said what?
Who introduced this game here?
He.
You started this game.
At the beginning, the Brazilian.
Yesterday we were playing in the Gobernador products
So the Brazilian.
Yes, the Brazilian.
or the Portuguese.
The Brazilians, Portuguese is the name.
Brazilians.
The Portuguese is también also.
Okay. From Portugal.
Okay. And are you from?
Pakistan. Muhammad from Pakistan.
Oh, okay. Thank you. This boy is from Ecuador, Cuba.
Cuba.
Hey, you need to get your hand down.
Down.
Sorry.
Bye. It's nothing related with eggs.
Lo hago porque sé que les
Same effect.
I want to see the funny.
Yeah.
I want to see the fun. Funny guys playing. Yeah.
Siéntate, es que hacen así.
Every time you start,
No, aparte los chicos están muy aguados ahorita.
Sí que no te quieren morir.
No es cierto. Agarraron la onda chido, pero pues la chava ya los tenía bien aleccionaditos.
Ok.
Por eso. Porque ya ni los peló. Ella como que le laten los normas.
¿Ahí este lo regresaron o? Te vas a quedar con él.
Tengo que.
Ok.
Pero no quiero quedarme con la chica en la habitación. Estoy sola. Que abrieron la puerta hace ratito y un olor rarito en la
Ok.
habitación y yo así de...
Mejor no preguntes qué era. A ver, chico. Está bueno, ¡Adiós!
because I never do this. I never do this. Okay, let's continue with what? I was thinking on this, but
Esta no soy yo, vos.
Ay, y él.
Ah. nos vamos?
Ahorita hay un autobús que sale, pero no todos se van. O sea, los chicos se van hasta las 4 y todos.
Es el ¿qué número de autobús se va? ¿L1?
Todos los L's. No todos, un L o dos. Los demás se quedan.
Ah.
Se pueden ir hasta las 4 y 4. Ay, sí, pero sí está como quieran.
Aguanta, ahorita les digo.
Pero me va a pesar. Pero estoy muy feliz. Ok, tú avisas en el camión que... Tú avisas que yo me quedo.
Samuel, te quedas. Es que ya se van de líder, eso ya te vas.
Dame 5 minutos para pensarlo.
Pero ya se va.
Ah, ya se va, ¿verdad? ¿Eh?
¿Verdad que sí?
Lo voy a dejar solo.
¡Quédate! ¡Ay, fumado!
Disfruto torturando todo.
No, es divertido, de eso se trata. Mira qué aguado es.
Ah, es que no te dije.
Chocolatera, vai para outro lado. Chocolatera.
experiment and theory played an essential role. The experiment, as you will see, is essentially a clock comparison experiment. One is comparing one of nature's clocks, a distant pulsar, a member of our galaxy but not very close to the solar system, and the very best standards of atomic time here on the Earth. And from that clock comparison experiment, established the existence of a phenomenon predicted by Einstein's relativity theory when published in 1915, but not previously observed, that is, the phenomenon of gravitational waves. If you could put the next slide on, please. The general content of the talk then will be divided into three parts. Can you have the next slide? I'll begin with an introduction to pulsars. There's no particular reason that everyone in this room should know what I'm talking about before we do that, and it's important that you have a general feeling for what these objects are like. They are astronomical objects distant from the Earth, and they have this clock-like characteristic which makes it so important for this particular experiment. I will then describe the experiment to you in some detail, and finally say a few words about the gravitational waves which the experiment has established very clearly must exist. So first, to put us in an astronomical frame of mind, the next slide will show a picture of an astronomical object, a supernova remnant. This one happens to be known by the name the Crab Nebula. It is the remains of the outer layers of a star which exploded in the year 1054. It was observed, in fact, in this part of the world, almost certainly by Mayan astronomers. It was observed in the Far East by Chinese, by Korean, by Vietnamese astronomers. It was not observed with any professional status in Europe simply because that was a time at which that kind of work in Europe was not being pursued. It was the Dark Ages. In the middle of this slide, you will see a pair of stars close together. And let me get my pointer ready to go here. Two stars close together here near the center. And in the next slide, you will see that the one to the lower right, can we have the next slide, is in fact an object which, in a sort of cartoon-like drawing, looks something like that. It's a strongly magnetized, rapidly rotating object known as a neutron star, which generates beams of radio noise which go outward along the directions of the magnetic poles. Just as is true for the Earth, the magnetic axis is not aligned with the rotational axis, and therefore, as the star spins, its magnetic field wobbles, rather like my hand is doing here. And that will mean that if one is located at some distance away with a radio telescope, perhaps up in this direction, one will observe a blip of radio noise each time the star makes one full rotation. Can we have the next slide, please? Here are a few facts about neutron stars. They are, sorry, back up, previous one, yeah. There are, the object has a mass about 1.4 times the mass of the sun, a radius of only 10 kilometers. A neutron star would fit inside the city of Merida. They're tiny objects, even though they are more massive than the sun. That means the density is extraordinarily high. It is not the density of atomic matter, but rather of nuclear matter. 1 teaspoonful of neutron star material weighs about 1 billion tons, 10 to the 9 tons. Astonishing. They are strongly magnetized, sorry, back up. These objects are strongly magnetized, and as I said, they generate radio noise. If you could click on the button here and let us hear the noises.
El del medio.
About once every 7/10 of a second. That's the actual noise that you hear if you connect an audio amplifier to the radio telescope output and just listen to it. Let's do the next one. This is also, okay. This one rotates much more rapidly. About 11 pulses per second. The last one, which is one of the fastest known pulsars, it rotates about 642 times per second. So it's a high-pitched audio tone. Let's do this one. Thank you. You can go to the next slide. All of you students work out the amount of kinetic energy represented here. It'll stop in a minute. Okay. All of you students could work out the amount of kinetic energy involved here. Right? You know how to work out the moment of inertia of a sphere and work out 1/2 I omega squared. Omega for a frequency of 642 hertz would be 2 pi times that number. You can work it out as a huge energy. If we had that amount of energy available here on Earth, there would be no shortage of energy, no reason to be worried about the price of oil or other things that concern us today. Well, pulsars are fascinating objects to study, but their signals are weak, and that means you need a large radio telescope with very sensitive receivers. The next slide shows a photograph of the giant radio telescope in the northwest corner of the island of Puerto Rico, near the city of Arecibo. Could we have the next slide, please? This telescope is a 1,000 foot, 300 and some meter diameter reflector in a more or less natural depression in the ground. It is a fixed mirror looking straight upwards. It can be directed to different points in the sky by moving the feed point antenna, which which collects the radiation reflected from the main surface. It's interesting to note that the telescope is built in a depression which is a cenote, a sinkhole. Geologists refer to these things as karsts. They are sinkholes created by the heavy tropical rainfall dissolving the limestone underground and creating giant caves which sometimes collapse, producing these sinkholes. The telescope was built in one of these sinkholes. The telescope itself is a reflecting surface made of perforated aluminum panels with holes in them, and the next slide will show us what it looks like underneath. You can actually walk down underneath the telescope. Can we have the next slide, please? You can see down here on the valley ground that ordinary vegetation grows. Here is the reflecting surface. It is held down to the ground by cables that tie into concrete anchors at the bottom, which help to maintain the accurate surface of the mirror. The next slide will show us a close-up view of the feed arrangement. Incoming signals, remember, are reflected from the surface and then back up here toward this region. They can go either into this long, thin antenna on the right or into a radome, which covers and keeps rain out. A number of other antennas and receivers, which are all in this region. So basically, the signals come in and are received at one or the other of these locations. This member rotates around a central bearing up here. You can see the circular rotation track, and each of the feed arrangements is located on a carriage which moves along a track, so that the antenna can be steered in azimuth by rotating around this track, and in the other angle, so-called zenith angle, by moving these two carts outward from the center toward the edges. In the next slide, you will see what it looks like from the triangle. You can go up there, you can ride a little cable car up to the where the antennas are located. You can also walk up along a catwalk that's shown here. As you look out toward way up to the top of the picture here, you can see just the beginning of the Atlantic Ocean. We're looking here away from Mexico, so we're not seeing the Caribbean, but rather the North Atlantic. Remember, this telescope is located not that far from here, about 1,000 kilometers in the northwest corner of Puerto Rico. The next slide will show us a photograph looking up inside the radome. You can just see a large box inside which the receivers are located. And the very next slide will show us what the telescope looks like at night. Can we see the next slide, please? At nighttime, it looks something like this, with some lights on to avoid any problems with airplanes. Well, that's the basic instrument. Now, a few more words about pulsars as astronomical objects. In the next slide, you will see a graph showing the number of pulsars that were known at any particular time, going back to late 1967, when the first one was discovered by a graduate student and her supervisor at Cambridge University in England. The number increased slowly for a few years, and then through some major effort that I was involved in, we increased the number by a lot in the late 1970s, and the number has continued to go up. As you can see, a few years ago it had reached somewhat more than 1,000 pulsars known, and the number continues to increase. It's now something like 1,700. In the bottom part of this graph, you can see the number of binary pulsars, pulsars that are orbiting around another star in a gravitationally bound orbit, like the Earth's orbit around the Sun, or the Moon's orbit around the Earth. The first one of those was discovered in 1974 in here, and they have also been discovered at increasing rates recently. The reason, incidentally, for the increased slope, the increased rate of discovery of pulsars in the last couple of decades is simply traceable to the advances in electronic instrumentation. Pulsars are objects which benefit greatly in their study by the use of digital electronics and computers, and that sort of thing has become much more straightforward in the last 20 years or so than it was 40, 30 years ago or more. The next slide will show us a picture of the distribution of pulsars on the sky. This is a map of the whole sky. The coordinate system is such that the plane of our galaxy, the Milky Way, is along the equator. And you can see that pulsars, like other types of ordinary stars, are concentrated along the plane of our galaxy. That's not surprising because they are members of our galaxy, not of some other galaxy elsewhere. They are strongly concentrated toward the direction toward our galactic center as well. And that's not surprising because the sun and the solar system are not very close to the galactic center. We're out near one edge of our galaxy. And so when we look for other objects, we see a very large concentration of them in the direction toward the center. That is why, of course, those of you who live in the southern hemisphere have a much brighter night sky with stars along the Milky Way than we do in the farther north countries. Because in the north, when the galaxy goes overhead, we are looking in the direction out of the galaxy instead of into the galaxy. One more slide of this type. The next one will show us a graph of the number of pulsars as a function of their rotation rate. A pulsar spinning once per second would be over in this region. And as you can see, most of them have periods around 1 second. The slowest rotating ones are up close to 10 seconds, and the very most rapidly rotating ones down around 1 millisecond, like the one that you listened to, which was about 1.5 milliseconds. You will notice that almost all of the binary pulsars are at the lower end of this graph. The ones that are shaded are the binary pulsars. And that is one of the reasons why our discovery of the first binary pulsar in 1974 was a difficult one. It was also a fast pulsar, and at that time, the computing electronics that we had to use on the problem were nothing like today's computing electronics. The next slide, in fact, will show you what those computers looked like. Here is my then graduate student, Russell Hulse, the man who shared the Nobel Prize with me some 20 years later. He's standing in front of the computer that we used for this experiment. It is, believe it or not, what we in those days referred to as a mini computer, but it's not very small, and it weighed about 700 pounds. Anyway, you can see that the electronics has come a long way since then. As part of his PhD thesis, Russell Hulse discovered a large number of pulsars. He detected 50 of them, in fact, with the Arecibo telescope, and that roughly doubled the number of pulsars that were known at that time. But one of the objects he discovered was by far the most important, and the next slide will show us why. Its period was not constant. It was almost constant, but not quite. It varied by about 1 part in 1,000 over a cycle which repeated, as you can see, every 7 3/4 hours, just a little bit less than 8 hours. Any of you students here could do the simple calculation to work out what the pulsar's velocity is in this orbit. You would take the total difference in period divided by the average period, as I've shown down here, and you would get a number equal to the velocity of light, the velocity of the pulsar divided by the velocity of light. And I've worked out here to put the scale of the graph in velocity of the pulsar in kilometers per second. This object is moving at 300 kilometers per second in its orbit, an astonishingly large velocity, and one which told us right away that this object would be potentially an interesting relativity laboratory, one in which the laws of gravitational relativistic physics would be important in order to trace its orbit accurately. The reason for that is shown in the next slide. We, of course, are, here we are with the sun. B stands for the barycenter of the solar system, the so-called center of mass. Here we are on the Earth, going around the sun in an orbit. Here is the pulsar going around another object in its orbit. We're at some distance. The distance changes because of the Earth's position in its own orbit and because of the pulsar's position. All these things need to be taken into account if we want to compare the accurate ticking of the pulsar clock as it freely rotates on its axis with the very best standards of atomic time that we have here on Earth. Here are the expressions that are important. One that has to do with the ordinary Doppler effect, or simply, if you like, the changing distance between the pulsar and the Earth. Here we have the second order effects, which arise because of basically special relativity effects, things which have to do with the velocity of the pulsar divided by the speed of light squared, and by some general relativistic effects which have to do with the masses of all of the other objects in the solar system. Finally, we have an additional time delay, which arises because of the fact that in relativity, light rays do not travel precisely in straight lines as they would in Euclidean space, but are curved when they go past massive objects. When the pulsar is on the back side of its orbit and the other star is on the forward side, we would expect the pulsar signals to be delayed a little bit by that effect, and we would have to account for that as well. One of the effects of all of these applications of the principles of relativity to this experiment are that the realization that this pair of stars should not remain in an orbit of fixed duration forever. Rather, the orbit should gradually lose a little bit of its energy. That will cause the two stars to move a little closer together, and that will cause the period of the orbit to grow slightly shorter. Now, the next slide will show us that effect in a very schematic form. As the two stars orbit around each other, according to relativity, gravitational waves should be generated. Those waves should carry away energy and angular momentum. There will be a loss of energy, which means the orbit must shrink, and a calculation suggests that the orbit should shrink by the tiny amount of about 1 millimeter per orbit. The size of the orbit, it's off the top here, but so you can't read it, but it is approximately 1 million kilometers. So the orbit shrinking by 1 millimeter, where the total size of the orbit is 1 million kilometers, that would seem to be much too small to have any hope of being able to observe. But fortunately, that's not quite true, because we can hope to observe the effect by measuring a small change in the orbital period. And experimentally, this is a good point to keep in mind, those of you who may choose to do experimental physics in the future. Experimentally, when you can reduce the measurable quantity of your experiment to something which is either a time, a duration of time, or a frequency, you can sometimes make extraordinarily high precision measurements. Times and frequencies can generally be measured to very high accuracy, and that turns out to be true in this case. Now, you might wonder whether in an experiment like this it would be possible to do an experiment to detect the presence of gravitational waves in the laboratory instead of in an astrophysical context. And if so, you might guess this would be an advantage. In the laboratory, after all, you can design the equipment yourself. You can measure the masses, measure the sizes, measure all the things that you would need to do in order to calibrate the experiment. You can, in fact, make it as well suited to the task as you would like. And therefore, wouldn't it be better to generate gravitational waves in the laboratory rather than like the way that Heinrich Hertz did for electromagnetic waves and detect them perhaps at the other side of the laboratory or at the back of the room? Wouldn't that be a good way to do such an experiment? And the next slide will show us, I think, why that is not the case. Einstein published a paper in 1916, I think you can just about read that at the top of the screen, in which he had recognized by that time that his new theory predicted the existence of a form of radiation that had never before been observed. He realized that if you made a large mass, perhaps a strong, long steel bar, and put it on the shaft of a motor and spun it very rapidly, you should generate a quantity of gravitational radiation. And you can calculate from the theory how much that should be. And it turns out to be that the luminosity of such a gravitational wave transmitter in gravitational waves should be given by this expression. M is the mass of this bar, A is its length, omega is the angular frequency of rotation of the motor. Okay, we could do that calculation easily enough. G is Newton's constant. As we know in the units we normally use, that is a very small number. And, whoops, bad news. C is the speed of light, of course. It's in the denominator, and it occurs here to the 5th power. If you put G over C to the 5th, you've got a tiny number, so that any reasonable numbers you can imagine creating in a laboratory for an experiment like this would produce a tiny amount of radiation. For a steel bar of radius 1 meter, of length 20 meters, of mass about 500 tons, spun at a very rapid rate, say 30 radians per second, that's just short of the tensile strength of steel that would break the bar at that point. And how much radiation do you get? I hope you could read it way down at the bottom of the screen. The luminosity in gravitational waves would be about 10 to the negative 22 ergs per second. It's tiny. It's not even, no hope whatever of being able to detect that. Even worse, from the experimental point of view, the receiver that you would have to generate to receive this quantity of gravitational waves would also have this same expression in front of its coupling constant. And so there's no hope whatever of doing a gravitational wave experiment in a laboratory now or in the foreseeable future. The next slide shows us why it is possible to do this experiment in an astrophysical context. If we have a pair of stars rotating, say, around their common center of mass, the way these ones are pictorially supposed to be doing, then we can work out, we can actually use Kepler's law to eliminate A from the previous equation and plug it in. I won't go through the details, but it ends up that the luminosity and gravitational waves for a star, a pair of stars orbiting like this, should be given by the total mass of the system, m1 plus m2, divided by 2.8. That, in fact, is the appropriate mass of the observed binary pulsar is about 2.8 solar masses, times the period to this ratio, times about 10 to the positive 31 ergs per second. And as you probably know, that's a number which is not time ratio to a useful amount. The output from the signal averaging process is a series of blips like this, one for each of the frequency channels in the receiver. It happens that all of the remaining boxes in this picture, the ones that are connected by green lines, are connected with the timekeeping aspects of the experiment. And those are the things which need to be kept very accurately. There is a local observatory clock which keeps time as well as we can at the observatory. That clock is an atomic clock. It's accurate to about 1 microsecond per day. That is good enough, more than good enough for the observations to take place, but over longer periods we can actually even track the small drifts of that clock compared to distant, more accurate standards of time by using the GPS satellites. I'm sorry again, the label of that object has been cut off, but that's supposed to be a satellite. We have our receiver at Arecibo receiving signals from GPS, and you all know about those things today. They were rather unusual when we started this work back in the early 1980s, but they're much more common today. So we can effectively keep time at Arecibo to very high accuracy. Now, the analysis of the data looks like the next slide. We have as input the observed TOAs, or times of arrival of the pulsar signals. Okay, we record those waveforms, we measure the distance over to where the pulse is. That combined with the start time of the signal averaging process tells us the time of arrival the measured time of arrival of the pulse. So we have all of those. Topocentric means at the observatory, centered at the observatory. We have to keep track of that carefully because, of course, the observatory is not a fixed location in space. It's fixed on the surface of the Earth. The Earth is rotating, the Earth is moving around the sun. All those things have to be taken into account. We have clock corrections, as I just described. We have a model of the solar system. I think the tops of those words are cut off, but we need to know exactly where the Earth is in space relative to some essentially fixed standard, an inertial reference frame. For that purpose, the center of mass of the solar system, the so-called barycenter, is a useful approximation. So we need a model of the solar system which will tell us the position of the Earth with respect to the center of mass of all of the planets, as well as the Sun. We need to account for the fact that the rotation of the Earth on its own axis is not quite at a constant rate. After all, the Earth is not a rigid sphere. It has oceans and atmosphere that are all sloshing around, so that it has a molten core as well, and that's not fixed. So the actual rotation speed of the Earth changes a little bit from time to time. The length of the day, in other words, may vary by up to a millisecond. That's why every few years we may have a so-called leap second, where your clocks are effectively delayed or advanced by 1 second to catch up with the rotation of the Earth. Anyway, all those things need to be accounted for. And then there is an overall model that tells us, this is a computerized code now, which knows about the equations of motion for the pulsar in its orbit around another star. And out of this process come a set of model parameters, also very important to the experimentalist, a set of so-called post-fit residuals, or the difference between the measurements and essentially what the prediction of the theory is based on the fitted model parameters. So I'll say just a few more words about the parameters. On the next slide, you'll see a list of the actual parameters describing the orbit of this pulsar as they would be determined on the basis of Newtonian physics alone. Essentially just applying the laws of Kepler as developed further by Newton. Here they are then. Here are the Keplerian parameters. There's the orbital period of the system, the eccentricity, the direction of the major axis relative to some fixed direction, and the time at which the pulsar and its companion object reach their closest point of approach. Finally, there is the projected distance of the projected length of the semi-major axis of the elliptical orbit. Sine I here appears because there is no way to determine from these, what essentially are Doppler shift measurements, what is the inclination between the plane of the orbit and the line of sight. And so what we get is a projected semi-major axis. Okay? We can determine, after having found all these parameters, which we can do easily from the observed data, we can observe this quantity, sometimes referred to as the mass function. It doesn't tell us separately what the mass of the pulsar is, or the mass of the other object, M2, but it tells us this combination between them and the inclination angle, sine I. And that altogether, that gives us some restrictions on what the nature of the system must be. But that told us, in fact, right away, even before we could do any relativistic measurements, that told us that the system was consistent with a mass of about 2.8 solar masses for the total. In other words, about twice the expected mass of a neutron star, which is already by theoretical grounds expected to be something like 1.4 times the mass of the Sun. Fortunately, things are even better though, because we can make some relativistic measurements. And the next slide will show us the relativistic parameters, which in principle can be determined. I refer to these here then as the post-Keplerian parameters, according to the theory of general relativity. It would be just perfectly possible also to produce a similar set of equations to these for some other competing theory of relativistic gravity, if and when such a theory is worthy of exploration. But right now, Einstein's theory remains the very best theory of gravity we have, so that's the one to which we want to apply our experimental results as accurately as possible. So what can we expect to measure? We can measure the rate of change of the angle of the major axis of the ellipse relative to the line of sight. The orbit is expected to precess gradually. The major axis, represented by my hand here of the ellipse, is going to gradually change its angle for the same reason that the planet Mercury famously advances its perihelion in the solar system. That was one of the very first tests that was applied to Einstein's theory. In fact, the experiment was known even before the theory was produced in that case. So we expect to be able to measure that quantity. We expect to be able to measure a quantity which characterizes the second order Doppler and gravitational redshift terms. We expect to be able to measure the rate of change of the orbital period, that is the shrinking of the orbit, but expressed here in a time like